in place. All right, now, I do want to warn you, Exam 2 was easier than Exam 2s in the past in this course. Primarily because we chopped off the rest of Chapter 16, this is the second half of 16. Actually, the hard stuff in Chapter 16. Okay? Chapter 17 is harder. All right? Just because you went up on this exam doesn't mean you can sit there and say, oh, okay, I finally mastered this, now I'm going to slack off. Because if you do, your grades will be right back up there again, or else right back down there again, compared the same as what they were on Exam 1. Okay? If you want to score the same score you did on Exam 2, on Exam 3, I think you're probably actually going to have to work a little bit harder than what you did for Exam 2. Mainly because the content is harder. Alright? Okay. So, I should have those grades posted sometime today. I can't make any promises. Okay, so, back to chemistry. Strong electrolytes. Remember from Chem 1, a strong electrolyte is something that completely and totally dissociates or ionizes in water to give charged species. It produces 100% of the stuff goes to produce ions. All right. So for us now, that would be strong acids, and here's our list of strong acids. All right. Strong bases. Here's our list of strong bases. These are our strong electrolytes for an acid-base chemistry. All right. They completely ionize or dissociate in solution, meaning that 1 mole of the starting material gives me 1 mole of the ion in solution. Period. In other words, if I have a bottle of hydrochloric acid that says 1 molar, that means I have a 1 molar concentration of protons in solution. I have actually no HCl in solution because it's a strong acid. It completely ionizes. Right, bases are the exact same thing. All right, now weak electrolytes, remember weak electrolytes were those things that only partially ionized or partially dissociated in water. All right, these are our weak acids and our weak bases. All right. Now their strengths are related to their Ka or Kb value, and we'll see that again today. They only partially ionize. In fact, the degree of ionization is dependent upon 2 things. Their Ka, Kb value, and the initial concentration. We saw that yesterday, as the percent ionization went up as the initial concentration went down. All right. Meaning we're going to have to do equilibrium calculations here. Istables. Luckily, for the most part, all of the istable calculations in this chapter, well, in this section of the chapter, can be done by a extra small approximation or a successive approximation. All right? And that's pretty much going to be true from here on out. All right? You may run into one that you have to use a quadratic on, but we'll show you how you can avoid doing that as we get to that part. Okay, so conjugate acid-base pairs. We introduced these in the very first section of this chapter. All right, where basically an acid gives up its proton, it becomes deprotonated, and it becomes a conjugate base. All right. Well, there are strengths to these things. Not all conjugate acids and bases are strong or weak. They're not all the same strength. Okay. Now, a strong acid has, I'm going to go with what the textbook says, has a weak conjugate base. But I want you to remember that very up there. Okay. A strong acid has a very weak conjugate base. It is a conjugate base by definition, but it does not act like a base. Okay, for example, hydrochloric acid reacts with water to give me hydronium plus chloride. I wrote this as a one-way reaction for a reason. Effectively, 99.99% of the hydrochloric acid, or HCl, is in an ionized form. Okay, this reaction goes pretty much all the way, 0.001% of it does not react, or does not dissociate. Effectively, it's 100%. Okay? So if I was to try to figure out the strength of the chloride anion, which it has been deprotonated, meaning it's a conjugate base, if I wanted to look to see what its strength was, I'd react it with water and see what the value of this equilibrium constant is. Okay? That would be a Kb value. Well, I got news for you. That reaction does not go forward at all. Okay? Chloride, I can take chloride and put it in water, and I am not going to get hydrochloric acid and hydroxide out of it. Okay? It does not happen. All All right? That reaction does not proceed. In fact, the only way this reaction goes is backwards, does not go forwards. Because chloride, while it is technically a conjugate base, it is a weak conjugate base, it does not ionize with water itself. That's where the very comes in. Very is in very weak. In fact, it's a conjugate base in definition only. It does not act like a base in water, other than the fact that it's deprotonated. Okay? So this thing only goes backwards. All right, now, weak acids, though, on the other hand, have relatively, notice the relatively is not capitalized, but I still have relatively strong conjugate base. They are conjugate bases, so HAC, actinium, does not care if I'm going to use AC to represent acetate. So you're going to see a lot of AC in the next chapter and a half. AC means acetate. Acetic acid ionizes with water to give me hydronium plus acetate. Okay? Acetic acid is a weak acid. Now, if I take acetate and react it with water, I'm going to get some acetic acid back in hydroxide. All right? Meaning this reaction, well, this reaction does go forward. It does have a measurable Kb. Okay? So acetate does, in fact, act as a base. Right? It is the conjugate base of a weak acid, meaning that it is a relatively strong conjugate base. Right? So, it does ionize with water. Okay, so the stronger the acid, HCl is the example up here, the weaker its conjugate base. All right? So, strengths of conjugate acids and bases. Strong base has a very weak conjugate acid. Sodium hydroxide gives me sodium plus hydroxide. If I try to react that backwards, react sodium with water, well, sodium is already reacted with water if I have Na plus here. Right? Na plus water does not give me sodium hydroxide plus a proton. That does not go forward. In fact, sodium hydroxide will react with a proton to give me water plus sodium ion. It only goes backwards the way I have it written here. Why? Because sodium is the cation, is the conjugate acid of a strong base. But it's conjugate acid in definition only. It does not act like an acid. Okay? Weak bases have relatively strong conjugate acids. So ammonium plus water to give me ammonium plus hydroxide. We've been looking at this one for a while. You know this one has a measurable Kb. What happens if I put ammonia in with water? Well, ammonium plus water is going to give me hydronium plus ammonia back. All right? This one does go forward. Why? Because it is a relatively strong conjugate acid because it comes from a weak base. Okay? So again, the stronger the base, the weaker its conjugate acid. Okay? This is a strong base because this reaction goes forward completely. It does not want to go backwards. This guy here is a weak base because it goes forward and backwards. Meaning this one can also go forward and backwards. All right? So, the stronger the base, the weaker its conjugate acid, and therefore the weaker the base, the stronger its conjugate acid. We can quantify these strengths. Remember that Ka and Kb are a measure of how strong a weak acid or weak base is with respect to one another. All right? So, since acetic acid is an acid, has an ionization constant Ka, acetic acetate is the conjugate base of acetic acid, so I can react that with water and measure the Kb now, because acetate here is acting as the base. Okay, it's a proton acceptor. It's accepting a proton from water to give me acetate plus hydroxide. All right? So I'm going to call this Kb because this is a base reaction. Ka because this is an acid reaction, or this is producing an acid, this is producing a base. When I add those two reactions together, notice what I get. Two waters in equilibrium with hydronium plus hydroxide. Well, that's Ka. I'm sorry, that's Kw. Well, we would expect that the product of two big Ks is equal to, we multiply the two big Ks together, we get the overall K for the reaction. Right, that is nothing more than equilibrium constant algebra. All right, so Kw tells us the relationship between the strength of the weak acid and its conjugate base, or the weak base and its conjugate acid. Kw is equal to Ka times Kb. Well, technically at 25 degrees C. All right. Now, the same rule that applies to pH and pOH is true here. pKw is equal to pKa plus pKb. And at 25 degrees C, that is equal to 14. All right. So you can see a strength of a conjugate acid strength of a weak acid or weak base listed as pKs instead of just as Ks. All right. So the smaller the value of Ka, the weaker the acid, the stronger its conjugate base. We see that now quantitatively. Smaller the value of Kb, the weaker the base, the stronger its conjugate acid. All right, so there is a give and take here between the strength of the acid and its conjugate base, or the base and its conjugate acid. Okay, so what is the Kb of the acetate ion if the Ka of acetic acid is 1.8 times 10 to the minus 4? Well, the relationship between Ka and Kb is that Kw is equal to Ka times Kb at 25 degrees C. If it doesn't specify a temperature, assume it's 25 degrees C. All right? We're looking for Kb, we're looking for the base constant for acetate. How strong of a base is acetate? So we want to solve this for Kb, so that is equal to Kw divided by Ka, 1.0 times 10 to the minus 14, divided by 1.8 times 10 to the minus 4. I cheated. To 2 sig figs, 5.6 times 10 to the minus 11. It's not a very strong base, but it is basic. Okay? Which all the problems are. Well, we can do another one. Let's do it for ammonium. How strong of an acid is ammonium? Well, Ka is going to be equal to Kw divided by Kb. 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. 2 sig figs. 5.6 times 10 to the minus 10. Now, is there any rhyme or reason why ammonia and acetic acid have the same number in the mantissa? No, it's fluke. Makes them easier to memorize if you want to memorize them, but there's no reason to do so. These are easy calculations. All right, make sure you get these right on the upcoming exam. Well, when is the next exam? It's a ways. Okay, fairly straightforward calculations. Diprotic and polyprotic acids. Well, never mind, I should. We have another calculation to do. Okay. We've talked about diprotic and triprotic acids and polyprotic acids. We've mentioned that, for example, sulfuric acid only has one strong proton, the other one is a weak proton. All right? But what about things like phosphoric acid? What about things like carbonic acid, oxalic acid? All right. Not everything has just one proton. How do we treat it? Well, it turns out that it's a little bit more complicated than you might think. All right. So each of the protons has an associated Ka with it. All right, so carbonic acid, H2CO3. All right, that's what causes the bubbly in your soda. Gives me a proton plus hydrogen carbonate. Ka1, because I have a Ka associated with each of the protons. This is the first one. Ka1 has a numeric value. But the bicarbonate, or hydrogen carbonate, can give me another proton to actually give me proton plus carbonate. So Ka2. All right? So how do we do this calculation? Well, it's not very, well, Ka1 will always be greater than Ka2. It's always easier to pull a proton off of a neutral species than it is to pull a proton off of something that's already negatively charged. All right? So, here's a list of values for you for some common diprotic acids and a triprotic acid. Phosphoric is the only triprotic acid down here. Sulfuric acid, Ka1, the book just calls it very large. It does have a measurable Ka, but in water it completely and totally ionizes. Therefore, we don't define the Ka value for sulfuric acid. Oxalic acid is relatively strong. Sulfuric acid, relatively strong. Ascorbic acid, vitamin C, very weak. Carbonic acid, very weak. Hydrosulfuric acid, that would be H2S, relatively weak. Very weak second proton, 1 times 10 to the minus 19. Yikes. And then, of course, phosphoric acid, we have times 10 to the minus third, minus 8, and then minus 13 for that third proton. That third proton is probably not going to come off in water unless the concentration is very, very, very weak of the initial concentration of the phosphor H3PO4. Okay, so let's do a calculation here. All right. And these are probably, well, they're not the most complicated calculations you're going to do this semester, but they're definitely not easy. All right. This calculation requires 2 ice tables. Okay. Technically speaking, phosphoric acid requires 3. All right. So I'm going to start by writing H2CO3 in equilibrium with proton and bicarbonate. I'm going to go ahead and fill this out. This is 0.05. I'm not going to write down trailing zeros. I'll take care of sig figs at the end. We're going to assume that this is approximately equal to 0. This will be equal to 0. It's got to shift to products minus x, plus x, plus x, 0.5, minus x, x, x. So Ka1 is equal to 4.2 times 10 to the minus 7 is equal to x squared divided by 0.05 minus x. Okay, that's part of the problem. Now, this proton can also come off in solution. So I'm going to have to calculate its ice table. Bicarbonate ionizes in water to give me proton plus carbonate. This initial concentration is not 0. This initial concentration is x. This initial concentration cannot be assumed to be equal to 0. It's also equal to x. This one is 0. All right? So, we've already used one variable. This is obviously going to shift towards products. It's going to be minus y, plus y, y. So I'm going to have x minus y, x plus y, y. And this Ka2 is going to be x plus y times y divided by x minus y. Nasty. Okay. We're not going to make you solve this as a system of equations. Thankfully. Linear algebra, this is not. Instead, we're going to solve it one at a time. All right? So, this value of Ka, 4.2 times 10 to the minus 7. Where does this equilibrium lie? Towards reactants or towards products? Towards reactants. Meaning, this is probably not going to change much. So, what we're going to do is we're going to use the x is small approximation. And I'm going to approximate the value of that x. All right. So, I'm going to assume that my first x is equal to 0. I'm going to solve this for the black x. So that x is equal to 4.2 times 10 to the minus 7 times 0.05. I'm going to go ahead and put the minus x here, because that's going to be my iterator. So my first guess, x equal to 0. I plug that in, and I'm going to get a new value of x. That new value of x is going to be equal to 1.449 times 10 to the minus 4 when I plug that in. Now, when I plug this in here, I'm going to get another value of x. I'm not going to bother showing it, writing it all out. Why don't I call that x of I, because I'm iterating across that x. When I plug this number in for x, solve for the black x, my new answer is 1.447 times 10 to the minus 4. Okay. So, if I was to compare 1.5 to what? 500. Okay, I find out that it's well within my 5% limit. I'm going to go ahead and I'm going to pump it through one more time just to make sure that I'm converged. I change in the fourth digit. That's 2 parts in 10,000. Two parts in 1,000. I'm converged mathematically. I'm going to use that as my value of x. Okay? So, this is my value of x. I can now go plug in that value of x over here. Okay? So I'm going to have 1.447 times 10 to the minus 4 minus y. 1.447 times 10 to the minus 4 plus y and y. Okay, so solving for Ka2, 4.8 times 10 to the minus 11 is equal to 1.447 times 10 to the minus 4 plus y times y divided by 1.447 times 10 to the minus 4 minus y. Now, the value of this equilibrium is times 10 to the minus 11th. Which side does this thing favor, reactants or products? Very strongly so. Meaning, is this going to change very much? No. So what I'm going to do is I'm going to use the x is small approximation. I'm going to leave this number alone. I think this number is not going to change much. This number is not going to change much because it's the same number plus y instead of minus y. So really, I'm only thinking that this number is the only one that's truly important here for me to calculate. So I'm going to let that y, now I'm dealing with y is small instead of x is small approximation, but ultimately it's the same thing. So I'm going to let my initial guess be y is equal to 0. Solving this for y, I get 4.8 times 10 to the minus 11 times 1.447 times 10 to the minus 4 minus a y. I'm going to change colors here in a second. Divided by 1.447 times 10 to the minus 4 plus y. Okay? Now, I don't need a calculator to calculate my next value of y0. This times that, that's 0, so these two things cancel. My next value of y, y1, is 4.8 times 10 to the minus 11, which is my value of Ka2. So I'm going to plug that in and iterate and use this as my red y. And I'm going to get a second y. I just want to check to see what I get. And I get, again, to 2 sig figs, 4.8 times 10 to the minus 11. That is equal to Ka2. So, if Ka1 is greater than 1,000 times larger than Ka2, we're going to make some approximations here. Okay? First of all, I can calculate this concentration, which I did. Okay, so the concentration of my undissociated acid is equal to 4.99 times 10 to the minus 2. It barely went anywhere because I started at 0.05, which is 5 times 10 to the minus 2. Now, concentration of my bicarbonate effectively it doesn't change. I mean, I can go ahead and do the subtraction here. 1.447 times 10 to the minus 4 minus 4.8 times 10 to the minus 11. That's 7 orders of magnitude. Okay, 7 orders of magnitude is 10 million. 10 million. If I have $10 million, do you really think it's going to matter if somebody erroneously subtracts $4 from my account? I doubt I'd notice it. Okay? So, this concentration doesn't change. This concentration doesn't change. All right, so the concentration of bicarbonate is just simply equal to that from the first one. Concentration of my proton is effectively equal to that from the first one. Concentration of carbonate, we're going to say is equal to Ka2, which is simply equal to 4.8 times 10 to the minus 11. Now, if Ka1 is greater than 1,000 times bigger than Ka2, we don't need to do the second ice table. Okay? We don't need to do that second ice table. In that case, the concentration of A2 minus, that's the conjugate base of the completely and totally deprotonated species, is approximately equal to Ka2, and nothing changes after the first ice table. We solve the first ice table. Basically what this tells us is that my value of y is sufficiently close to 0 that I don't need to solve the problem on the second ice table. Okay? On the next exam, you will have a diprotic acid problem to solve. Well, if I was betting, I would say so. I can't make any promises because I may not write the exam in that section. All right. Okay. Now, we can only do this if Ka1 is 1,000 times greater than Ka2. Okay? That's 3 orders of magnitude. 3 orders of magnitude different. 3 orders of magnitude different. 4. Sorry, that's 3. That's 6. That's 7. That's 4. That's 11. That's 5 between the first and the second, and then it's 5 more between the second and the third. The only 2 on here that you cannot make this approximation are the first 2. Sulfuric and oxalic. You have to solve both ice tables for sulfuric and oxalic acid. Because this approximation doesn't work. Like it's only 3 orders of magnitude. 6.5, 6.1. It's not going to work. Okay. So, salt hydrolysis. Salts react with water. Really? Well, yeah. Especially if the ions that are produced when I dissociate it in water are the conjugate acid or the conjugate base of a weak base or a weak acid, respectively. Okay, they can produce hydronium and hydroxide. All right, so there are a couple of things we need to consider here. Cations. Cations are typically going to be conjugate acids of weak bases. Ammonium, for example, ammonium is a cation. Ammonium is the conjugate acid of ammonia. All right, those are going to undergo hydrolysis in water. All right, hydrated metals. Hydrated metals can also produce acids and bases in water. Hydrated metal. What happens is that the hydrated metal weakens the bond between oxygen and hydrogen to the point where water can come in and steal a proton. Okay? And the reason why is because aluminum is a relatively electron-poor metal. All All right, so it reacts with the lone pairs on the oxygen atoms, and it pulls that electron density towards itself, and weakens the bond between hydrogen and oxygen. I mean, water can do this by itself. Water can pull a proton off of another water and make hydroxide plus hydronium. It's called the autoionization of water. That's the basis of Kw. Aluminum helps that process, makes it easier, effectively. All right? And so hydrated metals, in this case hydrated aluminum, is acidic. All right? Now, the way we're going to determine the strength of how strong this guy is as an acid is by looking at charge density. Okay? Aluminum is a 3+ cation. But where is aluminum on the periodic table? Third row, meaning it's actually relatively small. And 3+ means that it's got 3 fewer electrons than it's supposed to have. It's going to be really, really small. Okay, it's going to be about the same cationic radius as helium. Maybe a little bit bigger. Very, very small with 3+ charge on the surface of that sphere. Meaning it's got a very large charge density. Very small surface area, very large charge, large charge density. It's going to be a relatively strong acid. All right. So group 1A and 2A, all except for beryllium, have too low of a charge density in their neutral metals. We've already seen what sodium plus does in water. All right. Sodium plus, we put it in water, nothing happens. It looks at us. In fact, sodium is almost always going to be a spectator. Sodium cation. All right. Beryllium, though, where's beryllium on the periodic table? Row 2. I take 2 protons off that thing, and those 4 electrons, I take 2 electrons off. Those 2 electrons that are left are being sucked towards a +4 nucleus. I guarantee you beryllium 2+ is smaller in diameter than helium. It's got a 2+ charge on it. That's a very large charge density. Beryllium acts as a acidic metal. All right. All other metals are weak acids other than group 1A and 2A, with the exception of beryllium. And the acidity increases with increasing charge density. All right. So which is going to be a stronger acidic metal? Iron 2+ or iron 3+? Stronger acid. 2+ or 3+? Iron. 3+, larger charge density. All right. Okay. Anions. Anions are typically the conjugate bases of weak acids, and they are therefore weak bases. Right. Acetate. Acetate reacts with water to produce acetic acid plus hydroxide. Okay? Meaning that acetate is a basic anion. Right, so let's predict the following. Ammonium nitrate. Here's the question. Where does ammonium come from? We're thinking in terms of acids and bases. We have ammonium and nitrate. What would ammonium come from? It's the conjugate acid of ammonia. Okay, is ammonia a strong acid or a strong base, or a weak acid or a weak base? Ammonia is a weak base, meaning that ammonium is a relatively strong conjugate acid. Nitrate, where does nitrate come from? Where does nitrate come from? Nitric acid. Okay? Nitrate comes from nitric acid. Now, is nitric acid a strong, weak acid or base? It's a strong acid. So, is nitrate a relatively strong or weak conjugate base? It's weak. In fact, it's not going to ionize. All right? Let me draw some pictures for you. I just thought I was done with the board. So, in order to predict whether we have an acidic or basic salt, we need to know where those ions came from in terms of acid-base chemistry. Okay, so we have ammonium nitrate. I don't care whether we're talking aqueous or not, it's an ionic compound. Ammonium is always soluble in water, and so is nitrate. So I guarantee you Those two species are soluble in pretty much any concentration. All right. Ammonium is the conjugate acid of ammonia. That's where ammonium comes from. This is a weak base, meaning that ammonium by itself will react with water to give me ammonia plus hydronium. Ammonium is the conjugate acid of the weak base ammonia. Ammonium will produce hydronium in solution by itself. Okay? Therefore, ammonium tries to make the solution acidic. Nitrate, on the other hand, comes from nitric acid. This is a one-way street because nitric acid is a strong acid. Nitric acid is a strong acid, meaning this is a one-way street. Meaning that nitrate plus water does nothing. Nitrate just sits there and looks at you. Nitrate is almost always a spectator. So nitrate is what we call and I never can spell neutral right. It's neutral. So overall, is this solution going to be acidic, basic, or neutral? It's going to be acidic. Okay. Cesium chloride. What happens when I dump cesium chloride in solution? Well, it's a chloride salt. What do we know about halide salts? Unless it's silver, mercury, lead, it's soluble. So cesium chloride gives me cesium plus Cl minus. Okay. Where is cesium in the periodic table? Column 1A. It's column 1A cation. Column 1A cations are neutral. They don't react with water. What about chloride? Does it react with water? No, because it comes from the strong acid hydrogen chloride. So it is also neutral. So overall, is this salt going to be neutral or acidic? Neutral. Neutral, acidic, or basic. It's going to be neutral. And you might recognize its baby brother, sodium chloride. Go up a couple rows, you get sodium chloride. Sodium chloride is a neutral salt. Speaking of sodium, we have sodium acetate. Without going through the analysis, is that going to be neutral, acidic, or basic? Who says neutral? Who says acidic? Who says basic? Who didn't vote? Those of you that have your heads buried in your cell phones. Okay? The only thing here that can react with water is acetate. Acetate plus water to give me acetic acid plus hydroxide. That makes it a basic salt. Sodium acetate is basic. Iron chloride, iron 3 chloride. Acidic, basic, or neutral? Chloride's not going to do anything. Iron, we have a charged metal. All metal cations, except for column 1A and 2A, are acidic. Iron 3 chloride, acidic. That would be an acidic solution. What about ammonium acetate? We'll come back to that one in a second. Okay. Now you have another slide that has all these things listed on it all by itself. I left that there for by accident. Okay. We'll solve this problem that probably all the time we're going to have. You might be asked to quantitatively predict whether or not a solution is acidic, basic, or neutral. All right, so here's a question. What is the pH of a 0.1 molar sodium? What is OCl? What is OCl? It's one of those that you had to memorize on your polyatomic ions last semester. I'll give you a hint. It's the baby brother of ClO4. ClO minus. Hypochlorite. Sodium hypochlorite. Where do you think you find sodium hypochlorite? You find it on your shelf at home in your laundry room. Sodium hypochlorite is bleach. It's the active ingredient in bleach. Okay, so we need a pH of a 0.1 molar sodium hypochlorite solution. How do we do that? Well, we need to first, and this is always going to be the case, determine the ions in solution. Sodium hypochlorite, it's an ionic compound. It's going to be a strong electrolyte. We're going to get sodium plus, I'm going to go ahead and change that around, hypochlorite. Sodium comes from sodium hydroxide. Sodium is a charged cationic metal, but it's only a +1 charge. It is a neutral metal. It's a neutral cationic metal. It's not going to do anything in solution. Hypochlorite, on the other hand, will. Determine the strength of each species conjugate acid or base. Well, that one is a strong base. Therefore, it's not going to do anything with water. This guy, where does this guy come from? Hypochlorous acid. All right, hypochlorous acid is a weak acid. So this is going to be a relatively strong, weak base. All right. So if the conjugate of a strong acid or base, it won't affect the pH, meaning this is neutral. If conjugate of a weak acid or weak base, it will affect the pH, and we have to solve an ice table problem. Look at the Ka or Kb, the weak acid or weak base. The Ka of hypochlorous acid is 3 times 10 to the minus 8. So, what I need to do is I'm going to solve an ice table problem. Okay? So I have ClO minus aqueous plus water liquid is in equilibrium with hypochlorous acid and hydroxide. That's approximately 0. That's 0. We're going to ignore water. And this is going to be 0.1. Minus x, 0.1 minus x, plus x, plus x, x, x. So we're going to have the Ka for my acid is 3.0 times 10 to the minus 8. This is a Kb. Kb is going to be Kw divided by 3.0 times 10 to the minus 8. Kb is going to be 3.3 times 10 to the minus 7. Actually, this is a stronger base than, this is a stronger base. This guy's a stronger base than this guy is an acid. Okay. So, now we plug in the equilibrium values to solve for x. We're going to have 3.3 times 10 to the minus 7 is equal to x squared over 0.1 minus x. Which side is in his favor? The hypochlorite or the hydroxide? It's a very small value of Ka. So it's going to favor the reactants. Meaning, I'm going to do my x is small magic again. Meaning, this is going to be my small value of x. Alright, so my first small value of x is going to be 0, like it always is. I'm going to go ahead and solve for the black x. 3.3 times 10 to the minus 7 is equal to 0.1 minus that red x. If I plug in 0 here, my next value of x is going to be 1.826 times 10 to the minus 4. I'm going to plug that in again. And my next answer is 1.824 times 10 to the minus 4. It changed 2 parts in the 4th digit. I'm good. All right? So now that tells me my concentration of hydroxide. I'm asked for the pH. All right, well, pH is equal to 14.00 minus the pOH. So pH is equal to 14.00 minus a minus log, so it becomes plus the log of the hydroxide concentration, which is 1.824 times 10 to the minus 4. My pH is going to be 10.26. which allows us to quantitatively calculate the pH of a salt solution. It's a nice table problem. All right. One of the last thing I want to discuss depends upon the relative strength of conjugate acid or base. If Kb is stronger than Ka, it's basic. Ka is stronger than Kb, it's acidic. If they're equal, it's neutral. So my sodium acetate problem. Ka for ammonium is 5.6, Kb is 5.6, both times 10 to the minus 10. So sodium acetate happens to be a neutral solution. But sodium formate is going to be acidic. Sorry, basic. Sorry, ammonium formate is going to be basic. All right. So we will finish hydroxides and oxides next time on Monday and start chapter 17. Thanks for